Okay, so putting this all together. The needs for our model, what our model needed to be able to explain was temperature. We needed to have a model for explaining temperature. We needed a way to measure these temperature changes, really these energy changes as we found out. We needed to know, will this happen the same with other reactions? And is this only limited to chemical reactions? We needed to be able to represent our reactions. We needed to be able to draw out our molecules so that we could see this both in a written way and in a visual way. And we needed an explanation for how this could happen starting at room temperature. So let's start with represent the reactions. This is already something that we're pretty familiar with. We can write out a chemical reaction. Now we're going all the way back to our inciting incident of the barium hydroxide. So let's write that up here. Barium hydroxide being mixed with ammonium chloride. It's NH4Cl. I'm going to leave some space. You'll see why in a minute. And then my reaction happens. And what I get on the other side, is remember these two switch, and I got barium chloride, BaCl2, plus, and then my ammonium hydroxide mixed to create ammonia and water. It's all the same pieces, but that one hydrogen, so I went from NH4 to NH3, that one extra hydrogen, it decided to hitch a ride with the hydroxide. It's happier being water. Okay. So now I'm going to balance this real quick. If you want to go through and prove that I did in fact balance it on your own, go ahead. I know how much you all love to balance chemical equations. But we're just going to throw some 2's in here and we'll be balanced. Okay. So that's going to cover the part where we need to represent the reaction. However, how are we going to represent the temperature change in that reaction? More specifically, how are we going to represent the energy change in that reaction? Well, we know we changed energy. Some energy was moved around. And we know we got colder after the reaction. So did we gain heat or did we lose heat? Well, we gained heat over to here. We gained heat going through the reaction. We gained it from the environment. So we took heat away from the environment. So on the other side, there isn't excess heat. There isn't more heat on this side. There is less heat on this side. And so the way we write that is we're going to put plus heat. We're going to put this on the left side. The reason we put this on the left side is because we stole this. We stole this energy out of the environment. So the beaker, the air around it, the water that the beaker was sitting on all got colder. We robbed them of their energy in order to get this reaction to progress. Okay? So that's how we do it. We always put a plus heat. And now, if we were doing real chemistry with real thermodynamics, more advanced stuff, we would actually be able to go through and figure out what that exact number would be. But for our purposes, I'm only going to expect you to be able to put the heat into the reaction. Just write the word heat. Where is it being added? Is it being added over here so that these things pull heat away in order to get the reaction to go? Or is it being added on the other side? Is it being created and then let out into the environment, right? Okay. So now, let's tackle our next thing. Let's draw these molecules. That's what we wanted to work on today. We wanted to look at these in terms of Lewis dot diagrams. If you remember how to draw those, our first step is just going to be to write the element. And to write out barium hydroxide, I'm going to put brackets around each ionic substance. So barium is going to be Ba. I'm going to put brackets around it. That's how I know it's contained. It's all contained in here. And that was a 2+. And then it's got 2 hydroxides. So in order to do that, I'm going to draw out the hydroxide. I'm going to put an O connected to an H. Then I'm going to put a little minus because it's a minus charge. I'm going to put brackets around that whole thing. Okay? And there's two of them, so I'm going to draw two of them. So another O to H minus. I didn't draw them both the same size. Not that big of a deal. Okay, then I'm going to put a plus on. I'm going to put that in a different color. Speaking of, I'm going to try and keep these things separate, so I'm going to draw a little dividing line right here. Okay. Let's just keep that open. All right, ammonium chloride. Now I've got two of these, so I'm going to draw two of them. So first, draw out the ammonium, NH4. That means I'm going to have 4 H's around this. And it's going to have a positive charge. I'm going to get a big old bracket around it. I'm going to have a little bracket with a Cl minus in it. Then I'm going to draw another one. I'm going to draw all of my chemicals out here. You guys should draw this in your notes as well. So we all have the same model written down. Okay, so these are all of the chemicals I start with. I'm going to put another plus sign right here. Even though these are identical, I just want to make sure that I'm separating out which things are actually combined. Okay, so then I'm going to go down here. Let's still use purple for that. So what I'm going to have on the other side, I'm going to have barium chloride. I'm still only going to have one of those. So barium, still 2 plus. This time he's got 2 chlorines, which each are minus. See, that's where my 2 chlorines went, right here. Okay. And plus, my next substance is going to be 2 ammonias. So I've got N, H, H, and H. I'm going to put brackets around that, though that is a neutral substance. It doesn't have any extra charges. I'm going to draw another one right here. Okay, and then last but not least, we've got our water. Draw another one. Okay. So here's all of the Lewis dot diagrams for this. So I'm able to draw the molecules out. There we go. We were using purple for that. Let's be consistent. Okay. Now what else? Well, we still want to represent the energy change here. So let's put that in as well. We use blue for that. We use blue for that up here. Let's use blue for it down here. So plus heat. All right. And now that we've drawn this out, I wonder if we can see where did that heat come from? Where did that change in energy come from? Because remember, our energy needs to be conserved. Let's see if we can figure that out. What were the 2 types of energy we could have? We could have kinetic. So we could have kinetic energy, and I'm gonna put a little box around this so I can do some writing. Okay. So we could have kinetic energy or potential. What type of energy is temperature? Well, if we remember, our model for temperature was that these molecules are whizzing around at different speeds, and the hotter they get, the faster they move. The colder they get, the slower they move. So that would be kinetic energy. Even though we can't see them moving, we know that they are. We have kinetic energy there. So temperature is kinetic energy. So when this thing lowered its energy, it lowered its kinetic energy, that had to go somewhere else. It had to go to potential energy. Where is the potential energy in this model? Well, it's contained in these bonds. You see these little dashes here. Those bonds have energy. There's also energy in these ionic bonds, but that's not going to play as big of a role here. Let's see if we can see where those bonds changed. Now, if we're looking at this, well, up here I've got NH4. I've got 4 H's. Down here I only have 3 H's around the nitrogen. So what changed is these hydrogens left the nitrogen and attached to the oxygen. Notice here, this OH right here, that's my hydroxides. Those are my hydroxides up here. So this hydrogen went over to the oxygen. I wonder, what is the amount of energy contained in there? This is where this big fat textbook came in handy. I was actually able to look up the energy contained in these specific types of bonds. Nitrogen to hydrogen and oxygen to hydrogen, these are really common bonds, so they are in this handbook. Something like this barium to hydroxide, this barium to chloride, those are harder to find. I tried looking online, I wasn't able to find them that quickly. Really, it's because these processes really aren't that important. These though, these are very well known, they're widely used. So knowing the bond energies here is very important and it's very common. And so I actually looked these up. The bond energy right here, the energy contained in this bond, the potential energy in this chemical bond is 428 kilojoules, that's 1,000 joules per mole. Okay, remember a mole is trillions upon trillions, that's 6.022 times times 10 to the 22nd. Okay? The energy stored here, that is 314 kilojoules per mole. So now we can see where that extra energy went. So I have a difference here of 114. So this difference, if I take 428 minus 314, I get 114. So this difference, there's a difference of 114 kilojoules per mole. Well, that's what this number right here would be. So while I'm going to expect you guys to just write heat here, we could come in here now because we know the difference in these potential energies. We know that we had to rob 114 kilojoules for every mole of kinetic energy. So those are just numbers that we're able to throw in there. So that's 114 kilojoules per mole. Now remember the other day when we calculated how much energy it would take to raise or lower the temperature of water, well, if I went through and did these calculations, I could figure out how much of this reaction I would need to do in order to freeze a certain amount of water. That's how we're able to make things like ice packs. We're able to figure out how cold is it going to get and how long is it going to stay cold. We're able to create these products that are these instant ice packs. We can also make instant warm packs. We're able to figure out how hot is it going to get and how long is it going to stay warm. So those hand warmers, we want to know how hot it's going to get because if I break it and start using it and it gets too hot, it could burn my hand. So it's really important that we know the right amount of heat. So chemists really care about what this number is, okay? And that's how they're able to look at it. They're able to model this out just like we did here. And they're able to figure out what bond changes, what's the difference in the energy in those bonds. And it's just that potential energy, okay? It's just like if I have a rubber band and I pull it, I'm storing a certain amount of energy in there. If I pull it back like this, if I suddenly let it go, it's going to snap forward. That's really the same thing that's happening here. When these bonds let go, it snaps forward. It snaps and it starts to move other things around. This particular reaction what we're really doing, that kinetic energy from that water, from the substances around this that it's drawing out, is just like when I pull back the rubber band. Remember, because we're putting energy into the rubber band. Okay? So that's our model for these molecules. Well, that's great, because that answers a lot of questions here. So that answers our measurement. So we've got an exact way we can measure this. That is very exact. We have an understanding of why did this happen at room temperature? Well, it happened at room temperature because it had nothing to do with the temperature. It had everything to do with the energy. It happens at room temperature because we're converting kinetic energy into potential energy. Okay. Other reactions? This can happen with more than just chemical reactions because it's all about the transfer of that energy. That energy is going to be independent of these reactions, just like we saw when we dissolved the ammonium nitrate and the potassium hydroxide. Okay, great. So we've answered just about everything here. And just one last time, let's draw out our temperature model. I'm gonna use this space to do that. So I had a beaker. Let's give ourselves a little beaker here. This is the before, and this is going to be the after. And I'm going to go ahead and write in this number here because I like using the numbers. So this is 114 kilojoules per mole being removed. So from this environment, it's being removed. Okay. So then we're going to show that. I'm going to use different colors to show the different temperatures even more specifically. But really, the way we're going to want to show this is with these arrows that are pointing off in random directions. Let's draw 5 of them. Okay, and then when it got colder, our arrows got shorter. So here we go, let's do another 5. Alright, so there's our temperature model. We're able to see that these molecules are moving less. So look at all this stuff. I just want you guys to look at this. You should have a pretty decent understanding of how we arrived at all of these things. We've got 3 different ways we can describe this same phenomenon. And from the start, we had no idea how to put this information together, how to communicate what was happening with anything other than it got colder. We were able to say, yeah, it got so cold that it froze, but why? But what was happening? Well, now we could explain, well, kinetic energy converted into potential energy. These bonds absorbed more energy, and so it got colder because we pulled energy out of the system. So we have a good, full explanation for why this happened. That's great. All right. So, volcano. Let's draw it. So the official part of the video is done. I'm going to draw a volcano. I'm going to draw a Death Star. You're free to go. Here's our volcano. Let's say it's a volcano on an island. It's out at sea. And it's got lava. It's got lava pouring out of it. It's got smoke billowing up. Got fire shooting out of it. There's some purple in there, just for funsies. Great. So here's our volcano. Let's get a Death Star in there. See if I can draw it better this time. I think that's a pretty good circle. It's got that little weird band in the middle here. paneling. All right. Last but not least. No wonder the volcano's exploding. The Death Star's shooting it. There we go. There you go, guys. Death Star, volcano. Have fun.